Picture the first seconds of our universe, an unimaginable release of pure energy, a firestorm expanding faster than light itself, and within that chaos, something incredible was set in motion. The story of everything we are and everything we see began not in gentle whispers but in shattering violence. From that very first moment, the cosmos was shaped by titanic forces, by impacts of a scale so vast they defy human comprehension. We are all children of these cosmic collisions. Every atom in your body, every element that makes up our world, was forged in the heart of a dying star or the cataclysmic merger of ancient galaxies. It's a humbling thought, isn't it, that the iron in your blood was once the core of a supernova, and the calcium in your bones was scattered across the void by a neutron star collision billions of years ago. This journey we're about to take isn't just a tour of distant astronomical events. It's a voyage back to our own origins. We're going to explore 25 of the most monumental collisions that literally built the universe as we know it. These aren't just explosions, they are the architects of reality. They sculpted the first galaxies, they seeded the cosmos with the building blocks of life, and they continue to shape the fate of everything even today. We'll witness the colossal impacts that formed our moon, the violent mergers of black holes that ripple the very fabric of space and time, and the galaxy-smashing events that create dazzling new stars from the wreckage of the old. The scale is almost beyond belief, where entire solar systems can be torn apart and reborn in a single, breathtaking encounter. So get ready to experience the raw power and breathtaking beauty of a universe in constant, dynamic flux. This story is wild, chaotic, and profoundly beautiful. It connects each of us directly to the most energetic events since the dawn of time. As we count down these 25 massive cosmic collisions, remember that you are not just a passive observer. You are a living testament to their power, carrying the echoes of these ancient crashes within you. Let's begin our journey into the fury and the glory that shaped everything. At number 1 on our list, we must begin with the event that started it all, the Big Bang. But to truly understand its colossal nature, we need to correct a common misconception. The Big Bang wasn't an explosion that happened in space. Instead, it was the rapid, explosive expansion of space itself, everywhere at once. Think of it not as a bomb going off in a room, but as the room itself and everything in it, inflating from a single, unimaginably hot and dense point. This was the ultimate Genesis event, a moment where the concepts of before and outside lose all meaning. In the very first fractions of a second, the universe was a seething ocean of pure energy, a primordial soup where the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces were born and began to pull the cosmos apart. As this expansion continued and the universe cooled, that raw energy began to condense, colliding and coalescing to form the very first subatomic particles. Quarks joined to create protons and neutrons, which then captured electrons to form the first atoms. For hundreds of millions of years, the universe was a dark, featureless fog of this simplest matter, composed almost entirely of hydrogen and helium. It was from this sparse, elemental soup, forged in the fires of the Big Bang, that every star, every planet, and every living thing would eventually be constructed. The evidence for this astonishing beginning is all around us, etched into the fabric of the cosmos. The most compelling proof comes in the form of a faint, cold whisper that fills all of space, the cosmic microwave background radiation. This is the ancient light from a time when the universe was just 380,000 years old. Before that moment, the universe was so hot and dense that it was opaque, a glowing plasma where light was constantly scattered by free electrons. But as expansion cooled things down, electrons were captured by atomic nuclei, forming neutral atoms and suddenly allowing light to travel freely for the first time. That first burst of light has been stretching and cooling with the expansion of the universe for over 13 billion years. and today we detect it as a uniform microwave signal coming from every direction in the sky. It's the cosmic afterglow, a baby picture of the entire universe, and its existence perfectly matches the predictions of the Big Bang theory. The precise temperature variations in this background radiation, tiny ripples of hotter and colder spots, are like cosmic fingerprints. They represent the first seeds of structure, the slight gravitational overdensities that would, over eons, pull in more and more matter, eventually becoming the galaxies and galaxy clusters we see today. So, when we look at the cosmic microwave background, we are not just looking at evidence for a theory. We are directly observing the cooled remnants of the most massive and foundational collision of energy and space-time in history, the event that set the entire cosmic timeline in motion and made our existence possible. Moving from the universe's birth to the story of our own cosmic backyard, we arrive at a collision so violent it literally reshaped our world and created the familiar companion we see in our night sky. At number 2 on our list is the monumental event known as the Theia impact, the cataclysm that gave birth to our moon. Picture the early solar system, a chaotic and violent shooting gallery of protoplanets and debris. Around 4.5 billion years ago, a newly formed Earth was still a molten ball of rock, its surface a seething magma ocean. Then came Theia, a rogue planet roughly the size of Mars on a catastrophic collision course. This was not a gentle sideswipe. Theia slammed into the young Earth at an oblique angle, an impact of almost unimaginable force. The energy released was so immense that it effectively vaporized Theia and a significant portion of Earth's own mantle and crust, blasting a colossal cloud of superheated rock and metal vapor into space. In the immediate aftermath, a donut-shaped ring of incandescent debris, a cynesture, swirled furiously around what was left of our planet. Within this tempest, physics took over. Particles within the debris ring began to collide and stick together in a process known as accretion. Within perhaps just a single century, this material coalesced under its own gravity, assembling into the spherical body we now call the Moon. This theory, known as the giant impact hypothesis, elegantly explains so many of the quirks we observe. For instance, lunar rocks brought back by the Apollo missions show that the Moon's composition is strikingly similar to Earth's mantle, particularly in its isotopic fingerprints, as if it were made from the same source material. It's also much less dense than Earth because it formed primarily from the lighter rocky crust and mantle that were blasted into orbit, leaving Earth's dense metallic core largely intact. The legacy of this ancient crash extends far beyond just giving us a beautiful night light. This collision was a fundamental architect of the Earth we know today. The immense energy of the impact likely completely remelted our planet, resetting its geological clock and possibly initiating the plate tectonics that continually renew our surface. Most profoundly, the Moon's gravitational influence acts as a steadying hand on Earth's axial tilt. Without our large satellite, Earth's tilt would wobble chaotically over time, leading to wildly unpredictable and extreme climate swings that would make the stable, cyclical seasons we rely on for agriculture and ultimately for complex life impossible. So, the next time you look up at the Moon, remember you are witnessing the enduring scar of a planetary-scale disaster, a catastrophic birth that, in the long run, became the very key to creating a stable and habitable world. As we continue our journey through the cosmic collisions that forged our reality, we find that the violence of the early solar system was far from over. Following the monumental impact that created our Moon, the inner planets entered a period of sustained chaos known as the Late Heavy Bombardment. Imagine, for hundreds of millions of years after the planets themselves had mostly formed, the inner solar system became a target range once again. This wasn't a single event, but a protracted storm of asteroids and comets slamming into worlds like Mercury, Venus, Mars, and our own Earth. The evidence is written all over the Moon, whose ancient, heavily cratered highlands are a frozen record of this violent epoch. So, what caused this second wave of destruction? The most compelling theory points to a grand gravitational dance among the giant planets. As Jupiter and Saturn migrated through the young solar system, their immense gravity acted like a cosmic slingshot, destabilizing the vast populations of rocky and icy debris left over from planet formation. This sent a hail of material careening inward, pummeling everything in its path. For a young Earth still cooling and with its first primitive oceans perhaps just beginning to form, this was a time of both utter devastation and incredible possibility. While these impacts would have sterilized the planet's surface repeatedly, they may also have been the delivery system for two of life's most crucial ingredients, water and prebiotic organic compounds. The very comets and water-rich asteroids that were crashing into our world could have been the celestial tankers that filled our oceans and seeded the chemistry that would eventually lead to life. It's a profound duality, a period of extreme violence that simultaneously planted the seeds for a living, breathing planet. This entire cascade of events, however, leads us back to the gravitational master of our solar system, the king of the planets, Jupiter. To understand how such a colossal world came to be, we arrive at our fourth colossal collision event, the rapid and violent birth of Jupiter's core. In the solar system's swirling protoplanetary disk of gas and dust, the standard model of planet formation is a relatively slow, steady process of dust grains sticking together, then pebbles, then rocks, building up over millions of years. But for a gas giant to form, you need a solid core massive enough to start rapidly pulling in the vast amounts of hydrogen and helium gas that surround it before that gas dissipates. How did Jupiter's core grow so big, so fast? The leading theory suggests a process far more dramatic than slow accretion, a runaway collision of planetary embryos. Picture not just pebbles and rocks, but dozens of objects already the size of Mars or even larger, all orbiting the young Sun. In the region that would become Jupiter's domain, gravitational interactions would have thrown these embryonic worlds into chaotic orbits, causing them to smash into one another with tremendous force. Instead of bouncing apart, these violent mergers would have combined their masses, rapidly building up a single, super-sized core. Think of it as a cosmic game of bumper cars where every collision results in the cars fusing into a progressively larger and more massive vehicle. Once this core crossed a critical mass threshold, perhaps 10 times the mass of Earth, it unleashed an insatiable gravitational hunger. It began to hoover up the surrounding primordial gas at a breathtaking rate, rapidly inflating into the gas giant we know today. This frenzied period of collisional growth was the pivotal moment that created the gravitational anchor of our entire solar system. Jupiter's immense presence went on to shape the fate of every other planet, influencing the asteroid belt, potentially hurling comets toward the inner solar system during the late heavy bombardment, and acting as a protective shield, gobbling up or deflecting many dangerous objects that might otherwise have threatened Earth. The very existence of our stable, life-friendly corner of the cosmos may hinge on those ancient, violent collisions that built the heart of a giant. If you thought the collision that formed our moon was dramatic, consider the fate of the innermost planet. Mercury presents us with a stark and puzzling silhouette against the Sun, a world that seems to have gotten its proportions all wrong. Unlike Earth, Venus, or Mars, which have relatively thin metallic cores wrapped in thick rocky mantles, Mercury is the cosmic equivalent of a massive iron cannonball with just a thin shell of rock clinging to it. Its metallic core makes up a staggering 60% of the planet's mass and about 75% of its radius. For comparison, Earth's core accounts for only about a third of its mass. So how did this bizarre structure come to be? The most compelling explanation points to a cataclysm even more violent than the one that struck our own world. The leading theory suggests that a young, fully formed Mercury, once similar in composition to its planetary siblings, was struck a near-glancing blow by a protoplanet perhaps 1/6 its size. This wasn't a clean merger like the Theia impact. This was a cosmic hit and run of epic proportions. The colossal energy of the collision didn't just vaporize part of the planet. It literally blasted most of Mercury's rocky mantle and crust into space, leaving behind a scarred and stripped-down remnant, a planet that is fundamentally a surviving exposed core. This ancient stripping event directly dictates the brutal and extreme conditions we observe on Mercury today. With most of its insulating rocky blanket torn away, the planet's remaining thin crust responds violently to the intense heat from the nearby Sun. This has led to the most extreme temperature swings in the entire solar system. During the Mercurian day, surface temperatures can soar to 430 degrees Celsius, hot enough to melt lead. But without a substantial atmosphere to trap that heat, it all radiates back into space during the long night, allowing temperatures to plummet to -180 degrees Celsius. That's a 600-degree temperature swing. This relentless heating and cooling has also caused the entire planet's surface to contract over billions of years, wrinkling like a dried-out apple and creating giant, cliff-like fault lines called lobate scarps that run for hundreds of miles across the barren landscape. Furthermore, the identity of Mercury as a largely exposed core is key to understanding another of its mysteries: its weak yet global magnetic field. A planetary magnetic field is typically generated by a dynamo effect, the churning of a molten, conductive core. For a long time, scientists assumed that a core as large as Mercury's would have cooled and solidified completely long ago, especially on such a small world. But data from the Messenger spacecraft revealed the field is indeed generated by an active dynamo. The explanation, the giant impact that stripped the mantle, may have also flung lighter elements like sulfur and silicon into the core as the impacting object itself was vaporized and assimilated. These elements act like an antifreeze, dramatically lowering the melting point of the core's iron-nickel alloy and keeping the outer core in a liquid state to this very day, allowing it to slowly churn and generate that faint but detectable magnetic bubble. This single, shattering impact in the solar system's youth didn't just sculpt Mercury's physical form. It locked in the very conditions that define its hellish environment and its surprising internal activity, creating a unique world that stands as a stark monument to the violence of planetary creation. Continuing our tour of planetary wreckage, we arrive at a world that seems to have completely lost its sense of direction. While every other planet in our solar system spins like a top, more or less upright relative to its orbit around the Sun, Uranus rolls around the solar system on its side. Its rotational axis is tilted a staggering 98 degrees, meaning its poles point almost directly at the Sun during their respective summers. This isn't just a slight wobble, it's a fundamental reorientation, and the most likely culprit is another cataclysmic collision in the early days of our solar system. Picture the young Uranus, a nascent ice giant forming in the cold outer reaches. Current models suggest it was struck not by a small asteroid, but by a protoplanet roughly twice the mass of Earth. This wasn't a head-on collision that would have shattered the planet, but a powerful, off-center impact, a cosmic sideswipe that delivered a tremendous amount of angular momentum. Think of it like tapping a spinning billiard ball off-center. It doesn't stop spinning, but its axis of rotation is dramatically shifted. That single, monumental blow is thought to have knocked Uranus onto its side, setting it into its unique and seemingly clumsy roll for the rest of time. The consequences of this event permeate every aspect of the Uranian system. This extreme tilt creates the most bizarre seasonal cycle known in our solar system. For a quarter of its 84-year orbit, one pole is in constant sunlight while the other is plunged into a deep, frigid winter that lasts for 21 Earth years. Then, during the Uranian equinoxes, the Sun passes directly over its equator, leading to a more familiar but rapidly shifting cycle of day and night across the globe. This radical seasonal shift must drive atmospheric and climatic patterns that are utterly alien compared to anything we experience on Earth. with entire hemispheres heating and cooling over decades-long timescales. But the story doesn't end with the planet's tilt. The violence of that ancient impact didn't just reorient Uranus, it fundamentally reshaped its immediate environment. The colossal collision would have vaporized a significant portion of the impactor and Uranus's own outer layers, blasting a tremendous cloud of debris into space. This material, trapped by the ice giant's gravity, would have quickly settled into a disk orbiting its new, tilted equator. Just as the debris from Earth's impact with Theia coalesced into our moon, the material in this Uranian disk began to clump together, accreting to form its family of moons. And just as you would expect, these moons, along with any finer rings of dust and ice, orbit perfectly in line with Uranus's equator. Their entire orbital plane is tilted 98 degrees to the solar system's general plane, a permanent and telling piece of evidence locked in their path. This perfect alignment is the ultimate smoking gun. If the moons had formed alongside Uranus from the original solar nebula, they would orbit in a flat plane similar to the rest of the solar system. The fact that they orbit around its waist confirms they are the children of a much later and far more violent birth. So, the Uranian system, with its sideways world and its oddly orbiting moons, stands as a frozen monument to a single, defining moment of cosmic violence, a blow that literally knocked a giant on its side and used the wreckage to build a new celestial family. Now, let's consider a paradox at the very heart of our blue planet. After the fiery trauma of the moon-forming impact, Earth was almost certainly a desiccated, molten hellscape. The sheer energy of that collision would have boiled away any primordial oceans and stripped our young world of its early atmosphere. So, how did we become the water world we know today, a vibrant marble of blue and white swirling in space? The answer lies in a second, more nourishing wave of violence. We arrive at the concept of Earth's water being a gift delivered by celestial bombardment, primarily during the late heavy bombardment period. As Jupiter's gravitational shenanigans sent countless icy bodies careening inward from the outer solar system, our planet found itself in the path of a cosmic hailstorm. But this wasn't just a rain of rock, it was a delivery of life's most crucial ingredient. Two main classes of objects are thought to be responsible: comets and asteroids. Icy comets originating from the distant, frigid Oort Cloud and Kuiper Belt are like frozen time capsules from the solar system's birth, packed with water ice and complex organic molecules. Meanwhile, a specific class of asteroids, known as carbonaceous chondrites, which formed further out in the solar system where temperatures were low enough for ice to exist, are also incredibly water-rich. For hundreds of millions of years, these objects pummeled Earth, and with each impact, their icy contents vaporized on entry, eventually cooling and condensing to fall as rain, slowly but surely filling the vast depressions that would become our ocean basins. This theory, however, is not without its fascinating complications, leading to an ongoing detective story in planetary science. When scientists began analyzing the chemical fingerprints of water in our oceans and comparing them to the water found in different types of comets, they hit a snag. Measurements from distant comets like the famous Halley's Comet revealed that their water contains roughly twice the amount of a heavier hydrogen isotope called deuterium compared to Earth's ocean water. This deuterium to hydrogen ratio is a powerful cosmic tracer. If most of our water came from comets like these, our oceans should share that same high deuterium signature, but they don't. This forced scientists to broaden the investigation. More recent data from the Rosetta mission to Comet 67P Churyumov-Gerasimenko showed its water was even richer in deuterium, further complicating the picture. So, if not primarily from comets, then where? The evidence now points strongly toward asteroids as the dominant delivery system. Carbonaceous chondrite asteroids, samples of which we have in the form of meteorites, have a deuterium to hydrogen ratio that matches Earth's oceans almost perfectly. This suggests that while comets may have contributed a portion of our water, the bulk of it was likely carried by these water-rich asteroids that were flung into the inner solar system during the planetary migrations of the late heavy bombardment. The implications of this violent delivery are profound, turning a period of destruction into a moment of cosmic creation. Beyond just the water itself, these impacting bodies were also rich in other volatile compounds, including nitrogen, carbon dioxide, and critically, prebiotic organic molecules like amino acids. In essence, these asteroids and comets were not just water tankers, they were chemistry kits delivering the fundamental building blocks of life directly to Earth's surface. Imagine the scene, a scorching, sterile world, its crust still cooling, being bombarded by millions of icy rocks. With each impact, plumes of water vapor and complex organic material were injected into the nascent atmosphere. This relentless rain did more than just fill the oceans, it seeded the planet with the raw materials for biochemistry. In the warm, shallow pools and deep-sea hydrothermal vents that formed in this new aquatic environment, these delivered compounds could mix and interact, driven by geothermal and solar energy, eventually leading to the first self-replicating molecules. This means the very violence that once threatened to sterilize Earth ultimately provided the essential ingredients for life to spark into existence. The water you drink and the complex chemistry that powers every cell in your body are a direct inheritance from this ancient, epic rain from the heavens. Now, let's turn our attention to an impact that didn't just reshape a world, but completely rewrote the story of life upon it. At number 8 on our list is the Chicxulub impact, the collision that ended the age of dinosaurs and cleared the stage for a new cast of characters, one that would eventually include us. Picture the late Cretaceous period, 66 million years ago. In what is now the Yucatan Peninsula in Mexico, the day began like any other for the colossal creatures that ruled the planet. But in the cold darkness of space, a mountain-sized asteroid over 10 kilometers across was on a final, fatal approach. Traveling at a speed of around 20 kilometers per second, it slammed into the Earth's atmosphere. For the few brief seconds of its descent, the sky would have glowed with an incandescent fireball brighter than the sun. And then it struck. The energy released in that single moment is almost beyond human comprehension, equivalent to over 1 billion of the most powerful nuclear bombs ever detonated. The asteroid didn't just hit the surface, it punched straight through the Earth's crust, excavating a crater over 150 kilometers wide and 20 kilometers deep. The limestone-rich bedrock of the Yucatan instantly vaporized, hurling trillions of tons of superheated rock and sulfur-rich gas high into the atmosphere and beyond. The immediate fireball radiated outward, incinerating everything within a radius of nearly 1,000 kilometers. But the horror was only beginning. The seismic shockwave from the impact generated a colossal mega-tsunami, with initial waves perhaps over 1 kilometer high that radiated across the Gulf of Mexico, scouring coastlines and surging deep inland. At the same time, liquefied rock, blasted upward by the impact, began to rain back down across the entire globe. This fiery hail of molten debris re-entered the atmosphere, heating the air to oven-like temperatures and sparking spontaneous global wildfires that turned entire continents into a scorched, smoldering landscape. Yet the most devastating blow was still to come. It wasn't the initial fire or the waves that ultimately sealed the fate of the dinosaurs. It was the long, dark winter that followed. The impact had vaporized a huge volume of sulfur-rich anhydrite minerals from the Yucatan bedrock. This sulfur, combined with vast quantities of dust and soot from the global fires, was injected high into the stratosphere, where it formed a global shroud of fine aerosols. This pall effectively blocked sunlight from reaching the Earth's surface for months, possibly even years. Photosynthesis ground to a halt. The planet's food web from the base up collapsed. With no sunlight, temperatures plummeted globally. The lush, tropical world of the Cretaceous was plunged into a frigid, sunless state. acid rain formed from the sulfur compounds further poisoned the land and oceans. For the great dinosaurs and for about 75% of all species on Earth, this combination of immediate blast, global conflagration, and protracted, freezing darkness was unsurvivable. They were creatures built for a warm, green world, and they simply could not endure the abrupt, multi-pronged environmental catastrophe. This mass extinction event, known as the KPG boundary, marks one of the most pivotal turning points in the history of life. The disappearance of the dominant dinosaurs and many large marine reptiles left a vast array of ecological niches wide open. In the shadows of this global catastrophe, the survivors were small, adaptable, and often sheltered. Small mammals, which had scurried underfoot for millions of years, were perfectly poised to inherit this empty world. Their small size allowed them to hide in burrows, their warm-blooded metabolism helped them endure the cold, and their generalist diets let them find food where the specialized giants could not. In the millions of years that followed, these unassuming survivors diversified explosively, evolving into every form of mammal we see today, from bats to whales to primates. The Chicxulub impact was a tragedy of staggering scale for the life it erased, but it was also a moment of profound opportunity. Without that catastrophic collision, the evolutionary pressure that favored our small, furry ancestors would never have been applied. The dinosaurs might still rule, and the intelligent, tool-using mammals that would one day look up at the stars and piece together this very story would never have gotten their chance. Every human achievement, every city, every piece of art and science exists in the long shadow of that terrible, world-altering day. But if we're talking about literal earth-shattering impacts, we must journey to an ancient scar on our planet that makes even Chicxulub seem modest by comparison. Travel with me to South Africa, to a sprawling, weathered landscape known as the Vredefort Dome. What we see today are the deeply eroded roots of the largest and oldest confirmed impact structure on Earth. 2,023,000,000 years ago, long before dinosaurs ever walked the land, an asteroid of almost incomprehensible size screamed into our atmosphere. Current estimates suggest this celestial projectile was between 10 and 15 kilometers in diameter, potentially even larger than the dinosaur killer. Its speed and mass translated into a release of energy that is staggeringly difficult to quantify, a single event that unleashed more power than all the nuclear weapons on Earth combined, detonating simultaneously. The initial crater it left behind was not just large, it was colossal, originally spanning somewhere between 250 and 300 kilometers across. To put that in perspective, if such an impact happened today, it would have vaporized an area the size of a small country and fundamentally altered the global climate for millennia. The forces at play during the Vredefort impact were so immense that they did more than just excavate a hole. They transformed the very rock at the site, creating geological features that still baffle and amaze scientists. The most telling evidence is found in the unique shock metamorphism of the minerals. The instantaneous pressure exceeding hundreds of gigapascals and the incredible heat caused quartz in the bedrock to deform in ways that only happen during hypervelocity impacts, creating distinctive planar deformation features. The impact was so powerful that it pushed the Earth's crust downward, causing the deeper granite basement to rebound upward, much like a drop of water splashing back up after a stone is thrown into a pond. This rebound formed a central dome, a bullseye of uplifted ancient rock that is the structure's most defining characteristic today. After 2 billion years of erosion, what remains is not a classic crater bowl, but an inverted topography, a testament to the violence that turned the crust inside out. This geological crime scene provides the ultimate forensic evidence, proving that our planet's history is punctuated by catastrophes on a scale we can barely conceive. So what were the global consequences of this primeval cataclysm? The Earth of 2 billion years ago was a profoundly alien place. The atmosphere was largely devoid of oxygen, and life existed solely as simple, single-celled microbes in the oceans. An impact of this magnitude would have been a world-altering event for these primitive organisms. The immediate effects were likely a more intense version of the Chicxulub aftermath, a global firestorm, a dust-shrouded atmosphere blocking sunlight, and a potent impact winter. However, the long-term effects may have been even more profound and strangely paradoxical. While the initial darkness and cold would have been devastating for photosynthetic bacteria, the dramatic upheaval might have also set the stage for a major evolutionary shift. The colossal energy of the impact would have vaporized and blasted massive quantities of rock, releasing stored nutrients and minerals, particularly iron, into the global ocean. This sudden, massive fertilization of the seas could have triggered a dramatic bloom in the very microbial life that survived the initial disaster. Furthermore, the impact might have directly influenced the Great Oxidation Event, a period that began around the same time when oxygen-producing cyanobacteria began to significantly change the atmosphere. By shattering continental shelves and altering ocean currents, the Vredefort impact could have disrupted established ecosystems, allowing these new, oxygen-producing life forms to gain a competitive edge and ultimately transform the entire planet into a world capable of supporting complex, oxygen-breathing life. It's a fascinating and terrifying thought that one of the most violent days in Earth's history may have inadvertently helped steer the course of biology toward the diverse and complex biosphere we are a part of today. From the battered surface of Mercury to the tilted axis of Uranus, we've seen how single impacts can define a world's destiny. But perhaps no collision speaks more to a planet's lost potential than the one that may have turned a once Earth-like Mars into the frozen desert we see today. Mars presents us with one of the most striking geographical dichotomies in the solar system, a two-faced planet. The southern hemisphere is a rugged, heavily cratered highland, standing several kilometers above the average elevation. The northern hemisphere, by contrast, is an astonishingly smooth, low-lying plain that covers nearly 40% of the entire planet. This vast depression, known as the Borealis Basin, is so enormous that if you were standing on its rim, the opposite side would be well over the horizon due to the planet's curvature. The leading explanation for this planetary-scale deformity is a cataclysm of staggering proportions early in Mars' history. The theory posits that a protoplanet, perhaps the size of Pluto or even larger, slammed into the young Mars. This was not a mere glancing blow. It was a direct, devastating hit that fundamentally resculpted the entire northern hemisphere of the planet in a single, shattering instant. The mechanics of such an impact are difficult to fully grasp. The energy released would have been orders of magnitude greater than the impact that killed the dinosaurs. It wouldn't have just excavated a crater, it would have effectively blasted away a significant portion of the Martian crust and mantle in the northern hemisphere, leaving behind a continent-sized scar that plunged the landscape miles below the rest of the planet. The entire Martian globe would have reverberated like a bell, with seismic waves circling the planet and likely triggering massive volcanic eruptions on the opposite side, in the region now known as the Tharsis Bulge, home to the solar system's largest volcanoes. The material ejected from this impact would have rained back down across the entire solar system, and some scientists even speculate that certain meteorites found on Earth might be ancient fragments of Mars blasted into space during this very event. This single collision didn't just give Mars its distinctive look, it set in motion a chain of events that would rob the planet of its most life-sustaining systems. The most critical loss was likely Mars' global magnetic field. Today, Mars has only localized remnant magnetic fields locked in its ancient crust, but early in its history, it probably had a dynamo-driven global field similar to Earth. This magnetic shield is a planet's first line of defense against the solar wind, a constant stream of charged particles flowing from the sun. The Borealis impact, by obliterating such a huge portion of the planet's surface, may have delivered a catastrophic shock to Mars' internal engine. The immense heat from the impact could have disrupted the delicate thermal balance driving the convection in Mars' molten iron core. Without that consistent churning, the magnetic dynamo would have sputtered and died. As the magnetic field faded over the subsequent few 100 million years, the solar wind was granted direct access to the Martian atmosphere. Stripped of its protective shield, the atmosphere was vulnerable to being eroded away, particle by particle, slowly bled off into the void of space. This atmospheric stripping was the final, fatal blow to Mars' potential for life. With a thick atmosphere, Mars might have been able to maintain a greenhouse effect strong enough to keep water liquid on its surface. We see clear evidence that it once had vast rivers, lakes, and even a northern ocean that filled portions of the Borealis basin itself. But as the atmosphere thinned, the planet could no longer hold onto its heat or its surface pressure. The temperatures plummeted, and the liquid water either evaporated into space or froze solid, locking away beneath the surface in vast subterranean ice deposits. The planet's hydrologic cycle shut down completely. Without a magnetic field to protect it and a thick atmosphere to nurture it, Mars was doomed to become the cold, radiation-blasted world we observe today. The Borealis Basin, therefore, is more than just a geological curiosity. It is the ghost of a planetary trauma, a stark reminder of how a single, random collision in the chaos of the early solar system can irrevocably alter a world's fate, turning a potential twin of Earth into a frozen, silent tomb. And now, let's witness a collision that wasn't just studied in ancient rock layers, but one that unfolded in real time before the eyes of the world. At number 11, we have the spectacular saga of Comet Shoemaker-Levy 9 and its fatal encounter with Jupiter. The story begins not in 1994 when the impact happened, but a few decades earlier when this cosmic wanderer was likely captured by the immense gravity of the solar system's largest planet. Instead of orbiting the Sun, it became a temporary moon of Jupiter, trapped in a fragile, elongated orbit. Then, on a fateful pass in July of 1992, the comet ventured too close. It crossed Jupiter's Roche limit, that critical distance where the planet's tidal forces become stronger than the gravitational pull holding the object itself together. Jupiter's gravity didn't just tug on the comet, it exerted a differential force pulling the near side more strongly than the far side. This tidal stress was so powerful that it smoothly and inexorably shredded the comet's fragile, icy nucleus into more than 20 distinct fragments. When astronomers Eugene and Carolyn Shoemaker and David Levy discovered it in March of 1993, they saw not a single object but a breathtaking string of pearls, a line of brilliant cometary nuclei, each with its own glowing tail stretching across the sky. It was a staggering sight, a celestial body in its death throes, pulled apart by a force of nature and put on a very public display. The anticipation in the astronomical community was electric. For the first time in recorded history, we knew a major collision was imminent. The forecast was precise. Over the course of 6 days in July 1994, those 21 fragments, some over 2 kilometers across, would slam into Jupiter's southern hemisphere one after another. Every major telescope on Earth, and even instruments in space like the Hubble Space Telescope and the Galileo spacecraft on its way to Jupiter, were trained on the gas giant. And the show did not disappoint, as the first fragment, dubbed Fragment A, plunged into the atmosphere at a speed of 60 kilometers per second. It created a fireball so immense that it briefly outshone the entire planet in infrared light. The impact sequence was a relentless celestial bombardment. Each fragment would disappear behind Jupiter's limb, and moments later, a brilliant flash would erupt at the edge of the planet, signaling the violent release of energy. The plumes of superheated gas and debris that shot back out above the cloud tops were larger than Earth itself, glowing for minutes before raining back down into the atmosphere. The true legacy of the impacts, however, was written on Jupiter's face. The collisions left a series of massive, dark scars in the planet's upper atmosphere, each one a bruise the size of our entire planet. These weren't simple craters, they were enormous splotches of chemically altered material, created as the cometary fragments exploded and vaporized in the dense Jovian air. The debris injected into the stratosphere provided a direct, real-time laboratory for studying the composition of both the comet and Jupiter's hidden atmospheric layers. For weeks, these Earth-sized marks were easily visible from backyard telescopes, a humbling reminder of the raw power at play in our solar system. The event was more than just a light show, it was a paradigm shift. It gave us our first direct observation of a major extraterrestrial collision, providing a stunningly clear demonstration that such impacts are not just relics of a violent past, but ongoing processes in our dynamic cosmic neighborhood. It underscored Jupiter's role as the solar system's gravitational guardian, whose immense presence often draws in and destroys such potential threats, but also served as a sobering warning that Earth is not immune to similar civilization-ending events. We had a front-row seat to a force of nature that has shaped planets and wiped out species, a force that is as active today as it was 4 billion years ago. While the spectacular demise of comet Shoemaker-Levy 9 played out across the gulf of space, a much closer and more unsettling encounter had already occurred just a century earlier, serving as a stark reminder that our own world is not a sheltered spectator. On the morning of June 30th, 1908, in a remote and largely uninhabited region of Siberia near the Podkamennaya Tunguska River, the sky was torn open. Eyewitnesses dozens of miles away described a brilliant bluish fireball, as bright as a second sun, tearing across the heavens. It was followed moments later by a cataclysm that would become one of the greatest scientific mysteries of the 20th century. A massive explosion, equivalent to 10 to 15 million tons of TNT, roughly the power of a large modern hydrogen bomb, detonated in the air. The resulting shockwave was seismic in its force, registering on barometers as far away as England. It flattened an estimated 80 million trees across 2,000 square kilometers of dense forest, radiating outward from the epicenter in a stunning butterfly wing pattern of destruction. Trees at the very center were left standing but stripped of their branches and bark like a forest of giant charred telephone poles. The blast wave circled the globe twice, and for nights afterward, the skies across Europe and Asia glowed so brightly that people reported being able to read a newspaper outdoors at midnight, a phenomenon caused by vast amounts of ice crystals from the vaporized object suspended high in the atmosphere. For decades, the true nature of the Tunguska event remained shrouded in speculation, partly because the region's remoteness and political turmoil in Russia prevented a proper scientific expedition for nearly 20 years. When researchers finally reached the site in the late 1920s, led by the determined mineralogist Leonid Kulik, they were expecting to find a classic meteorite crater. To their astonishment, there was none. The epicenter showed evidence of immense burning and blast damage, but no significant impact crater and, more puzzlingly, no substantial fragments of a meteorite. This absence of a smoking gun fueled all manner of wild theories, from a miniature black hole passing through the Earth to the explosion of a crashed alien spacecraft. However, the most scientifically robust explanation, now widely accepted, points to a cosmic near-miss. The culprit was almost certainly a relatively small, rocky asteroid or a fragment of a comet, roughly 50 to 60 meters across. It wasn't the object's size that was extraordinary, but its speed and trajectory. Traveling at a velocity of perhaps 15 to 20 kilometers per second, it entered the Earth's atmosphere at a shallow angle. The immense pressure of plowing through the thick lower atmosphere at hypersonic speeds was more than the fragile body could withstand. It never reached the ground. Instead, it underwent a catastrophic airburst, disintegrating and vaporizing completely at an altitude of 5 to 10 kilometers above the surface. The physics of an airburst reveal why the Tunguska event was so devastating despite the lack of a ground impact. All the colossal kinetic energy, the object carried energy equal to 1,000 times the atomic bomb dropped on Hiroshima, was released almost instantaneously in a single massive point of heat and pressure. This created a supersonic blast of superheated gas that shot downward and outward, hammering the landscape below. This is why the forest was flattened so completely and why the trees at the very center, directly below the blast, remained standing. They were subjected to a primarily downward force, while the surrounding trees were knocked over by the outward traveling shockwave. Had this event occurred over a populated metropolitan area like London or New York, the entire city and its millions of inhabitants would have been utterly obliterated in a single, terrifying flash. The Tunguska event stands as a powerful case study in the difference between an impact and an airburst. It demonstrates that we don't necessarily need a direct hit from a dinosaur-killing asteroid to face a global catastrophe. A much smaller, more common object can still unleash continental-scale devastation if its explosive energy is unleashed in the atmosphere above a vulnerable target. This brings us to the most crucial implication of the Tunguska event: its role as a modern cosmic warning shot. The object that caused it was, in astronomical terms, remarkably small and faint, making it extremely difficult to detect with early 20th century technology. Even today, with our advanced telescopes and dedicated sky survey programs, we have identified only a fraction of the estimated population of near-Earth objects in that 50 to 100 meter size range. These objects are the most statistically likely impactors, striking Earth on average every few centuries to a millennium. An event like Tunguska today over a major city would not be just a natural disaster. It would be a civilization-altering crisis, causing unprecedented loss of life, economic collapse, and global upheaval. The silent, unseen danger of these objects is what makes planetary defense not a subject for science fiction, but an urgent and active area of scientific research. Initiatives like NASA, Planetary Defense Coordination Office, and international collaborations are tirelessly working to find, track, and characterize these potential threats, hoping to provide us with years or even decades of warning. The lesson of Tunguska is not one of past mystery, but of future vigilance. It was a tangible, recent demonstration that the processes which shaped the early solar system and occasionally reset the course of life on Earth are still very much in operation. Our civilization exists in a very real sense on borrowed time, nestled within a cosmic shooting gallery where the next major impact is not a question of if, but when. Just when we thought the lessons of Tunguska were a relic of the past, the cosmos delivered a brutal and very modern reminder. On a clear winter morning in February 2013, over the Russian city of Chelyabinsk, a previously undetected asteroid roughly 20 meters across screamed into the atmosphere at a staggering speed of nearly 19 kilometers per second. This was not a rare, deep space visitor. It was a common near-Earth asteroid, the kind we now know number in the millions. Its arrival was utterly silent and completely unexpected, hidden by the glare of the sun until the moment it began its death plunge. The visual spectacle was both terrifying and breathtaking. For a full 30 seconds, a fireball brighter than the sun streaked across the sky, its contrail a thick, white scar that lingered for hours. The immense friction and pressure of atmospheric entry caused the rock to violently fragment, creating a series of blinding flashes as pieces exploded in a cascade of light. But the true impact of the event was felt before anyone even looked up. The shockwave generated by the hypersonic passage and the multiple airbursts took several minutes to travel the distance to the ground. When it arrived, it hit the city of Chelyabinsk and its surrounding regions with the force of a tactical nuclear weapon. the blast wave shattered windows in thousands of buildings, sending razor-sharp glass flying across homes, schools, and offices. It collapsed sections of a factory wall and knocked people off their feet. In the end, over 1,500 people sought medical attention, most from these lacerations, making it the first documented cosmic impact to cause mass human injury in modern history. What truly set the Chelyabinsk event apart, and what cemented its place in the cultural consciousness, was the medium through which it was documented. This was the first major impact of the ubiquitous camera age. Russia's high rate of dashboard cameras, or dashcams, initially adopted to provide evidence in traffic disputes, inadvertently created the most comprehensive record of an extraterrestrial impact ever captured. Within hours, the internet was flooded with hundreds of videos from every conceivable angle: drivers on their morning commute, security cameras on buildings, even people filming from their apartments. The world watched in stunned real time as an ordinary day was violently interrupted by a force from the deep solar system. We saw the blinding flash illuminate the morning sky, the panicked reactions of drivers swerving their cars, and the terrifying moment the shockwave arrived, shaking cameras and blowing out windows. This was not grainy, distant footage or an artist's impression. This was visceral, immediate, and personal. It brought the abstract threat of asteroid impacts out of the realm of science fiction and Hollywood blockbusters and placed it squarely into the reality of everyday life. For the first time, the global public didn't just hear about the concept of an impact, they witnessed its shocking, disruptive power with their own eyes. The scientific analysis that followed this very public event was swift and revealing. The Chelyabinsk meteoroid was a stony asteroid, and the reason it caused such widespread damage despite its relatively modest size was its shallow entry angle. Much like the Tunguska object, it was primed for a catastrophic airburst. The main disintegration occurred at an altitude of about 30 kilometers, releasing energy equivalent to roughly 500 kilotons of TNT. The subsequent hunt for meteorites on the frozen ground below led to the recovery of a large fragment from Lake Chebaukal, which helped scientists pin down its composition and origin. Crucially, the event provided a devastatingly clear data point for planetary defense experts. It highlighted a critical and uncomfortable gap in our surveillance capabilities. Our major sky survey telescopes at the time were primarily focused on finding much larger, kilometer-sized objects, the civilization Enders. An object the size of the Chelyabinsk meteor, approaching from the direction of the Sun, was virtually invisible to our detection networks. It served as a stark demonstration that the most probable threat is not the global extinction event that happens once every 100 million years, but the regional or city-scale catastrophe that could happen at any moment with little to no warning. This sobering realization acted as a powerful catalyst for change. The Chelyabinsk impact injected a new sense of urgency and political will into the field of planetary defense. In its wake, funding and support for near-Earth object detection and tracking programs received a significant boost globally. NASA, a Planetary Defense Coordination Office, established just a year earlier, saw its mission underscored as a critical public safety priority. New and more powerful telescopes, like the upcoming NEO Surveyor Space Telescope, were fast-tracked with the specific goal of finding these smaller, yet still dangerous, objects, especially those that approach from the sunward direction, our primary blind spot. The event also spurred greater international cooperation, with space agencies around the world recognizing that a potential impact is a global problem requiring a unified response. Chelyabinsk was a violent and frightening event for those who lived through it, but for humanity as a whole, it was a necessary and transformative wake-up call. It provided the incontrovertible proof that the cosmic shooting gallery is still active, and that it is no longer a question of if we will be hit again, but when. The dashcam footage did more than just record a disaster. It gave us the collective push we needed to finally and seriously look up, to search the skies, and to begin the vital work of ensuring our civilization's long-term survival. Now we turn our gaze outward to a world that has become the very emblem of cosmic beauty, Saturn, with its breathtaking and iconic rings. But this stunning feature, a pristine halo of ice and dust, is not simply a decorative accessory. It's the glittering debris field of a long-vanished moon. The leading theory for their origin, often called the Proto-Saturnian moon collision, paints a dramatic picture of creation through destruction. Picture a moon, a substantial world several hundred kilometers in diameter, composed largely of water ice orbiting the young Saturn. For millions of years, it traced a stable path around its giant parent, but its fate was sealed by the relentless tug of orbital mechanics. As the moon's orbit slowly expanded due to gravitational interactions with other moons, or perhaps as Saturn itself evolved, it eventually crossed a fatal boundary known as the Roche limit. This is the distance from a planet within which the tidal forces, the difference in gravity's pull between the near and far sides of an object, becomes stronger than the object's own gravity. Saturn did not gently pull the moon apart, it subjected it to an irresistible stretching force. The icy body was smoothly and inexorably shredded, not in a single explosive instant, but in a prolonged, elegant unraveling. Alternatively, some models suggest a more direct and violent end, a high-speed collision with a rogue comet or a large Centaur object from the outer solar system. Either way, the result was the same: the complete disintegration of a sizable, icy world. This celestial demolition provided the raw material, but the transformation of that rubble into Saturn's exquisite rings is a story governed by precise physical laws. The countless fragments, ranging in size from tiny ice crystals to mountain-sized boulders, did not simply drift away. They were trapped within Saturn's gravitational dominance, their individual orbits dictated by Kepler's laws. The particles closer to the planet orbited faster than those farther out, and this differential speed caused them to begin colliding with one another. These collisions were not destructive, they were transformative. Over time, they smoothed out the orbits, grinding larger chunks into smaller pieces and spreading the debris into an incredibly thin, flat disk aligned with Saturn's equatorial plane. This is why the rings are so remarkably flat. Any particle on a tilted orbit would repeatedly cross the disk and eventually have its orbit circularized through countless gentle impacts. The brilliant whiteness of the rings is a direct clue to their composition and history. They are about 99% pure water ice, which is exceptionally reflective. This pristine quality suggests they are relatively young, perhaps only a few 100 million years old, as older rings would have been darkened by a constant rain of dark, carbonaceous dust from micrometeorites. The rings we admire today are therefore a temporary, dynamic structure, a vibrant and youthful scar from an ancient cataclysm, constantly being replenished and reshaped by the very collisions that formed them. The legacy of this event extends far beyond the rings themselves, influencing the entire Saturnian system in profound ways. The debris from the shattered moon didn't just form a passive disk, it created a new gravitational environment that continues to sculpt the planet's other moons. Some of Saturn's smaller, so-called shepherd moons orbit within gaps in the rings or along their very edges. Their gravity acts to herd the ring particles, clearing out specific pathways like the famous Cassini division and preventing the rings from spreading outward and dissipating over time. The rings also play a role in a bizarre atmospheric phenomenon. Instruments on the Cassini spacecraft detected a constant ring rain, a shower of tiny water ice particles from the rings, influenced by Saturn's magnetic field, falling into the planet's upper atmosphere. This means Saturn is slowly consuming the very remains of its former satellite. Furthermore, the presence of such a massive ring system affects the planet's own rotational dynamics and even its internal heat budget. The destruction of one moon and the creation of the rings set in motion a complex gravitational dance that continues to this day, a perpetual interplay between the planet, its rings, and its remaining family of satellites. The rings of Saturn are therefore not a static monument to a past disaster, but a living, breathing system, a cosmic laboratory where we can observe the processes of accretion and disruption in real time, a beautiful and violent chapter in the ongoing story of our solar system. As we consider the impacts that shaped our solar system, from the creation of our moon to the scouring of Mars, it's easy to think of our cosmic neighborhood as a stable and settled place. But the violence of collisions extends far beyond the scale of planets and comets, reaching up to the very architecture of galaxies themselves. In a discovery that rewrites our own galactic origin story, astronomers have uncovered compelling evidence that our Milky Way is not the pristine, isolated spiral it appears to be. Roughly 10 billion years ago, when our galaxy was still in its youth, it experienced a colossal merger, a dramatic embrace with a smaller dwarf galaxy known today as Gaia Enceladus, sometimes nicknamed the Sausage Galaxy for the distinctive, elongated shape of its star's orbits. This was not a gentle meeting. It was a head-on collision that fundamentally reshaped the Milky Way and left an indelible mark on the stellar population we see today. For a long time, the classic picture of our galaxy's formation was one of relatively peaceful, internal evolution, with stars forming from a slowly collapsing cloud of primordial gas. The halo of ancient stars surrounding the galactic disk was thought to be a quiet relic of that early era, but data from the European Space Agency's Gaia mission, which has been meticulously mapping the positions, movements, and compositions of over 1 billion stars, revealed a shocking truth. When scientists analyzed the trajectories of these ancient halo stars, they found a large group moving in radically different ways. Instead of orbiting in all directions like the rest of the halo, these stars were streaming along highly eccentric, radial paths, streaking in and out from the galactic center on sausage-like orbits that pointed to a single, violent origin. This stellar fingerprint was the first major clue, but the evidence didn't stop there. By studying the chemical composition of these stars, astronomers could perform a form of galactic archaeology. Stars that form in different environments have distinct metallic signatures, as they are forged from gas enriched by previous generations of supernova. The stars from the Gaia Enceladus galaxy were found to be noticeably different from the native Milky Way stars of a similar age. They contained a different ratio of elements, indicating they were born in a smaller, separate galaxy that had a slower and less efficient process of stellar evolution and metal enrichment. The timeline of the collision has been pieced together with remarkable precision. Before the merger, the young Milky Way was likely a more puffed-up, disordered collection of stars and gas. The inbound Gaia Enceladus galaxy, boasting perhaps a quarter of the Milky Way's mass at the time, was on a fatal course. When the two systems finally slammed together, the effects were transformative. The immense gravitational forces involved did not cause stars to physically crash into one another. The distances between them are far too vast, but the gravitational turmoil was extreme. The orderly motion of stars in the primordial Milky Way was thrown into chaos, and the incoming galaxy was itself completely torn apart, its stars scattered like cosmic confetti into a new, bloated halo around our galaxy. One of the most significant consequences of this merger was a spectacular burst of new star formation. The collision churned and compressed the vast reservoirs of gas within both galaxies, triggering gravitational collapse on a monumental scale. This event essentially gave birth to the galaxy's thick disk, the population of older stars that forms a puffy component above and below the main spiral arms we see today. A substantial fraction of the stars in this thick disk and a huge portion of the stellar halo were either born during this starburst or were actually donated by the devoured dwarf galaxy itself. In fact, it's estimated that as many as half of the stars in the Milky Way's inner halo originated from Gaia Enceladus. This means that when we look at a significant portion of the ancient, faint stars surrounding our galaxy, we are not looking at original members of the Milky Way family, but at the assimilated citizens of a long-vanished galactic system. The merger also likely played a crucial role in building the central bar and bulge of our galaxy, as the immense gravitational shockwaves funneled gas and stars inward, contributing to the structure we observe at the heart of the Milky Way today. This discovery fundamentally changes our understanding of our place in the cosmos. We do not reside in a galaxy that formed in quiet isolation. Instead, our Milky Way is a cannibal, a product of a violent and dramatic history of growth through consumption. The peaceful spiral we see on a clear night is the settled aftermath of a colossal clash that defined its very structure and stellar makeup. The Gaia-Enceladus merger is a powerful reminder that galaxy evolution is not a gentle process. It is a story of building and destruction, of chaos and rebirth on scales so immense they challenge comprehension. This single ancient collision set the stage for everything that was to come, including the eventual formation of our Sun and solar system in a quiet spiral arm billions of years later. Our entire cosmic neighborhood, it turns out, was built from the wreckage of a galactic disaster. Yet as we uncover the violent mergers that built our own galaxy, we are also staring toward a future cataclysm that will completely redefine our night sky. The next great collision is already written in the stars, a slow-motion dance of gravity that has been underway for billions of years. Our Milky Way and its nearest large galactic neighbor, the Andromeda Galaxy, are on an inescapable collision course, hurtling toward one another at a speed of about 110 kilometers per second. This isn't a random, chaotic event. It's the inevitable outcome of the mutual gravitational pull between these two cosmic titans, a pull so strong that it overcomes the overall expansion of the universe itself across the relatively short 2.5 million light-year gap that separates them. While the timescales involved are almost incomprehensibly vast, the first close pass is still about 4.5 billion years away. This future merger is one of the most certain predictions in all of astronomy, a fate that has been confirmed through decades of precise measurements of Andromeda's motion. So, what would this epic event look like from the perspective of a future Earth? The changes would unfold over billions of years, a celestial ballet in super slow motion. The first sign would be the Andromeda Galaxy itself growing steadily brighter and larger in our night sky. Today, it appears as a faint, fuzzy smudge to the naked eye, but as it draws nearer, it would transform into a breathtaking, structured spiral, eventually rivaling and then surpassing the apparent size of our own Milky Way band. As the two galaxies make their first close passage, they will not slam together like two solid objects. Instead, they will perform a complex gravitational tango, swinging past each other, their immense gravity stretching out long, shimmering tidal tails of stars, gas, and dust pulled from their outer regions. During this initial pass, the familiar structure of both spirals will be dramatically warped and distorted. The neat, orderly spiral arms will be pulled into chaotic, glowing streams, creating a spectacular, if temporary, celestial kaleidoscope. Our solar system's position within the galaxy will likely be flung onto a new, radically different orbit, carried along with the tide of stars from our galactic home. This brings us to the most common and understandable fear about such an event: the prospect of stellar collisions. It's a natural assumption that when two galaxies, each containing hundreds of billions of stars, slam into each other, the skies will be filled with exploding suns. But the reality is profoundly different and far less destructive to individual planetary systems. The key thing to remember is the incredible emptiness of galaxies. While they are unimaginably vast, they are mostly empty space. The average distance between stars in a galaxy like our own is about 5 light-years. To put that in perspective, if you shrank our Sun down to the size of a grain of sand, the nearest star would be another grain of sand over 4 miles away. When two galaxies interpenetrate, it's like throwing two handfuls of sand into a swimming pool. The chances of any two individual grains actually hitting each other are vanishingly small. For our solar system, the probability of being thrown into a path that brings us dangerously close to another star is astronomically low. The real drama of the merger is not in stellar fireworks, but in the gravitational upheaval that reshapes the very fabric of both galaxies. After their first dramatic close encounter, the two galaxies, now gravitationally bound even more tightly, will swing back around for a second and then a third pass. With each successive interaction, they will lose orbital energy, slowly settling toward the center of their new combined gravity well. Over the next 1 to 2 billion years following the first pass, they will repeatedly swing through each other, their structures becoming more and more blended and unrecognizable. The beautiful, ordered spiral disks will be completely destroyed. The final act of this multi-billion-year drama is the formation of a new single galaxy. The product of this colossal merger will likely be a large elliptical galaxy, which astronomers have playfully nicknamed Milkdromeda or Milkomeda. Elliptical galaxies are essentially the cosmic retirement homes for stars, vast, football-shaped collections of older stars with very little of the gas and dust needed to form new ones. The violent gravitational churning during the merger will have compressed and heated much of the galaxy's gas, triggering one last tremendous burst of new star formation that will consume the remaining fuel. Once that final starburst fades, Milkdromeda will settle into a quiet, reddish glow dominated by aging stars, a monolithic testament to a merger that began 10 billion years in the past. The legacy of this future collision extends beyond just the galaxies themselves. The merger will fundamentally alter the local galactic group, the small collection of galaxies dominated by the Milky Way and Andromeda. Their smaller companion, the Triangulum Galaxy, may also be drawn into the fray, either being swallowed by Milkdromeda or becoming a permanent satellite in orbit around it. On a grander scale, this event is a perfect illustration of the hierarchical model of galaxy formation, where the large galaxies we see today were built over cosmic time through a series of such mergers. Our own Milky Way's history, marked by the ancient Gaia-Enceladus collision, is simply a prelude to its final, most magnificent act. So, while the thought of two galaxies colliding sounds like the ultimate apocalypse, it is, in fact, a natural and creative process. It's the universe's way of building something new and grand from the old, a cosmic rebirth that will unfold on a scale of time that dwarfs all of human history, yet is as inevitable as the force of gravity itself. But to truly grasp the slow-motion dance of our own galactic future, we don't have to just imagine it, we can look out into the cosmos and see it happening right now, a preview playing out in real time. A stunning example of this is the celestial object known as the Antennae galaxies, a pair of spirals locked in a violent embrace roughly 45 million light-years away in the constellation Corvus. When you first see an image of them, the name makes perfect sense. Two distinct galactic cores, glowing with the light of billions of stars, are surrounded by a chaotic web of dark dust lanes and brilliant blue star-forming regions. And streaming out from this central chaos are two enormous, sweeping arcs of material stretching far out into the intergalactic void. These are the tidal tails, the antennae, that give the galaxies their name, and they are the direct and beautiful result of immense gravitational forces. The story of the antennae began a few 100 million years ago, a mere blink in cosmic time. These two spiral galaxies, likely similar in size to our own Milky Way, began their fateful approach. They didn't hit head-on initially, but rather swung past each other in a close encounter. It was during this first pass that the incredible gravitational tug-of-war began. The side of each galaxy closer to the other felt a stronger pull than the far side, and this difference in force, known as a tidal interaction, was enough to literally pull the galaxies apart. Stars, gas, and dust from their outer regions were stretched out, flung into long, graceful streams that we now see as those iconic antennae. This process didn't require stars to physically collide. The sheer power of gravity alone, acting across tens of thousands of light years, was sufficient to sculpt these colossal structures. These tidal tails are now cosmic fossil records, preserving the exact motions and dynamics of that first dramatic encounter. The real fireworks, however, were yet to come. After that first gravitational swing by, the two galaxies, now bound together by their mutual gravity, lost orbital energy and fell back toward each other for a second, more direct collision. This is the stage we are witnessing now. As the two vast clouds of interstellar gas and dust from each galaxy slammed into one another, they created immense shock waves. These waves of pressure raced through the galactic material, compressing huge pockets of gas to unbelievable densities. Just as squeezing a handful of snow creates a tight, hard snowball, compressing these cosmic gas clouds triggered a ferocious and widespread burst of new star formation, a phenomenon astronomers call a starburst. The antennae galaxies are now one of the nearest and brightest starburst regions in the entire sky. The evidence is in the brilliant blue-white light that dominates the central regions. This blue color is the signature of incredibly hot, young, massive stars that burn bright and live fast, exploding as supernova after only a few million years. Zooming in with powerful telescopes like Hubble reveals the stunning granularity of this stellar nursery. The central regions are not just a diffuse glow, they are peppered with thousands of brilliant young star clusters, each containing up to 1 million stars. These superstar clusters are thought to be the infant versions of the ancient globular clusters that orbit our own Milky Way today. We are essentially watching, in a single snapshot, the formation of an entire generation of stellar systems that will persist for billions of years. But this fertile chaos comes at a cost. The very same supernova that are created in this frenzy also blow apart the surrounding gas clouds, regulating further star formation and seeding the future interstellar medium with heavy elements. The antennae system is a roiling, dynamic ecosystem of creation and destruction happening on an epic scale. Observing the antennae galaxies is like being given a time-lapse preview of the Milky Way and Andromeda's future. While our galactic collision is still billions of years away, the physical processes at play are identical. We can expect our own serene spiral to be pulled into long tidal tails of stars, its neat structure warped beyond recognition. The calm pockets of star formation we see today will be replaced by a galaxy-wide firestorm of new star birth as our galactic gas reserves collide with those of Andromeda. The quiet, dark lanes of cosmic dust will be illuminated from within by the blaze of millions of new suns. The antennae show us that a galactic merger is not an end but a spectacular transformation. It is a violent, creative, and ultimately beautiful process where the old order is torn down to make way for something new. It is the universe's way of recycling its grandest structures, and in the antennae galaxies, we have a front-row seat to the breathtaking show. But what happens when the colliding objects are so immense that they're not just stars or galaxies, but entire clusters of galaxies, each containing hundreds of individual galaxies, vast oceans of superheated gas, and a gravitational field that dominates everything? This brings us to one of the most profound and elegant cosmic detective stories ever told, centered on an object known as the Bullet Cluster. This system, officially named 1E0657-5583, is the result of two galaxy clusters that have recently smashed into one another at a phenomenal speed. And within the aftermath of this titanic crash, astronomers found what many call the smoking gun for one of the universe's greatest mysteries, dark matter. For decades, the evidence for dark matter had been compelling but indirect. We could see its gravitational effects, the way it made galaxies spin too fast to hold themselves together, the way it bent the light from distant objects, the way it was essential for the very formation of cosmic structure. But we had never been able to separate its effects from the visible matter in a clear, direct way. The bullet cluster gave us that opportunity. It provided a cosmic laboratory where the different components of the universe were literally pulled apart and put on display for us to study. To understand why this collision is so special, we need to think about what makes up a galaxy cluster. The stars in the galaxies themselves, the part we can see with optical telescopes, account for only a tiny fraction of the cluster's total mass. A much larger portion, about 15%, is in the form of incredibly hot, tenuous gas that fills the space between the galaxies. This gas is so hot, reaching tens of millions of degrees, that it glows brightly in X-rays, and it's this X-ray emission that allows us to map its location. The remaining 85% of the mass, the dominant portion, is the invisible dark matter, which neither emits nor absorbs light of any kind. In a quiet, undisturbed cluster, all these components, the galaxies, the hot gas, and the dark matter, are mixed together, their gravitational pull all centered on the same point, making it impossible to distinguish their individual contributions. But in a violent, high-speed collision like the one in the bullet cluster, a remarkable separation occurs, revealing the fundamental nature of each component. The key to the whole discovery lies in how these different types of matter interact. The hundreds of individual galaxies within each cluster are mostly empty space. When the two clusters collided, the galaxies themselves, both the visible stars and the dark matter halos that surround them, passed right through one another with virtually no interaction. It's like two swarms of bees flying through each other. The chances of two bees colliding are incredibly small. The hot gas filling each cluster, however, is a different story. This gas is a plasma, a soup of charged particles, and it does interact strongly. As the two clusters slammed together, the clouds of gas from each one ran into each other head-on. This created a colossal shock wave, a cosmic sonic boom that heated the gas to even more extreme temperatures and, crucially, dramatically slowed it down through a powerful drag force, much like two clouds of smoke colliding and merging into a single turbulent mess. This is where the story gets truly fascinating. After the collision, astronomers were able to map the cluster using three different techniques. First, optical telescopes showed them where the stars in the galaxies were located. Second, space-based X-ray observatories like the Chandra X-ray Observatory mapped the location of the hot, interacting gas. And third, they used a technique called gravitational lensing to map the total mass, both visible and dark, by measuring how the cluster's gravity warps the light from even more distant galaxies behind it. When they overlaid these three maps, they saw something astonishing and completely unexpected by any theory that tried to explain the observations without dark matter. The two large clumps of mass, as revealed by the gravitational lensing map, were not centered on the bright, glowing cloud of hot gas. Instead, they were located precisely where the galaxies were. The bulk of the mass had neatly passed through the collision and was now far ahead of the gas, which had been left behind in the central region, stuck in a tangled, heated wreck. This separation is the definitive proof. It demonstrates with stunning clarity that most of the matter in the universe is not only dark, but that it is a substance that does not interact with itself or with normal matter through any force except gravity. It felt the gravitational pull of the collision, so it moved with the galaxies, but it experienced no friction, no drag, no pressure. It simply sailed right through the entire event. If the extra mass we were detecting was some modification to the laws of gravity, as some alternative theories suggested, then the lensing map would have shown the gravity centered on the gas, where most of the visible mass was concentrated. But it didn't. The gravity was clearly decoupled from the normal matter. The bullet cluster experiment showed us that dark matter is real. It's a physical substance, and it behaves as a collisionless fluid, a ghostly sea of particles that forms the underlying skeleton of the cosmos, upon which the visible universe is merely painted. It was a result that transformed dark matter from a compelling theoretical idea into an observational fact, forever changing our understanding of the fundamental composition of everything that exists. But while galactic collisions reshape the largest structures and asteroid impacts reset the course of life, there is another type of cosmic collision that operates on an entirely different scale, one of almost unimaginable density and consequence. At number 19 on our list, we turn to a spectacular event that answered a century-old question and literally forged the very elements that power our technology and adorn our fingers. This is the collision of two neutron stars. Picture the end state of a massive star's life after it has exploded in a supernova. What remains is no longer a ball of fusing gas, but a sphere of pure, degenerate matter so dense that a single teaspoon of it would weigh billions of tons on Earth. This is a neutron star, a cosmic atom smashed down to the scale of a city, typically only about 20 kilometers across, yet containing more mass than our Sun. Now imagine two of these incredible objects locked in a final, deadly gravitational embrace. They orbit each other thousands of times per second, rippling the fabric of spacetime itself with gravitational waves and slowly, inexorably spiraling inward. In August of 2017, after a journey of 130 million years, these ripples finally reached Earth, washing over our planet as a faint chirp detected by the LIGO and Virgo gravitational wave observatories. For the first time ever, we had caught the signal of two neutron stars merging, but the real revolution was just beginning. This gravitational wave alert triggered the largest astronomical follow-up campaign in history, and within seconds, telescopes all over the world and in space swiveled to the same patch of sky. What they witnessed was a kilonova, a brilliant, transient explosion of light that confirmed a monumental theory. This was not just the collision of two dead stars, it was the universe's primary forge for the heaviest elements in existence. The secret to this cosmic alchemy lies in the extreme conditions of the merger and a process known as the rapid neutron capture process, or the R process. To understand its power, we first need to grasp the limits of normal stellar fusion. Inside most stars, including our Sun, nuclear fusion builds elements by slowly adding protons step by step up the periodic table. This process can create elements from hydrogen all the way up to iron, but fusing atoms into anything heavier than iron actually consumes energy instead of releasing it, so fusion effectively hits a wall. For billions of years, the origin of elements like gold, platinum, uranium, and other heavy metals was one of astronomy's great mysteries. Supernovae were long thought to be the primary candidate, but their yields never quite matched the abundances we see in the universe. The kilonova provided the missing piece. When two neutron stars collide, they don't just quietly merge. The collision is catastrophic. It tears the stars apart, flinging a small percentage of their incredibly neutron-rich material out into space at velocities approaching the speed of light. In this ejected cloud, the conditions are perfect for the R process. A blizzard of free neutrons liberated from the shattered stellar cores bombards atomic nuclei. In a frenzied feeding frenzy that lasts only seconds, nuclei grab these neutrons faster than they can radioactively decay, building up super-heavy, unstable isotopes. These overstuffed isotopes then undergo a series of rapid radioactive decays, settling down into stable, heavy elements. It is in this brief, violent firestorm that the universe forges gold, platinum, neodymium for powerful magnets, and iodine essential for our biology. The observational evidence from that 2017 event was unequivocal and breathtaking. The kilonova's light curve, the way its brightness changed over time, told a clear chemical story. Initially, the explosion shone an intense, hot blue. This was the signature of lighter, so-called lanthanide-free elements being synthesized, but within a day, the color of the afterglow shifted dramatically to a deep, profound red. This red color is the telltale fingerprint of lanthanides, a group of heavy elements that include things like neodymium and europium, which have complex atomic structures that block blue light. The sheer amount of heavy material estimated to have been blown into space by this single event was staggering, many times the mass of our entire Earth, with a significant portion being pure gold and platinum. This one collision in a galaxy 130 million light-years away likely produced an amount of gold equivalent to several hundred times the total mass of our entire planet. It's a staggering thought that the gold in a wedding ring or a microchip was almost certainly born in a similar cataclysm, a blizzard of neutrons in the aftermath of a stellar collision that occurred long before our own solar system even formed. This discovery fundamentally rewrites our cosmic connection. We are not just made of stardust from long-dead suns. Our technology-rich civilization is built upon the ashes of the most violent and exotic collisions in the universe. The uranium that fuels nuclear power, the platinum that catalyzes chemical reactions in industry, and the gold that has driven human economies for millennia, they all share a common, spectacular origin. Without neutron star mergers, the periodic table would be a much emptier place, and the geochemical and biological diversity of our planet would be vastly diminished. These collisions are relatively rare, happening perhaps a few times per year in a galaxy the size of the Milky Way, but over billions of years, they have steadily enriched the interstellar medium with the seeds of planets and life. The 2017 event was a watershed moment, opening the new field of multi-messenger astronomy where we can both hear the space-time ripples of a cosmic event and see its luminous aftermath. It confirmed that the universe's most precious treasures are not forged in the steady fires of stars, but in the fleeting, unimaginably violent collisions of their ultra-dense corpses, scattering their riches across the cosmos to one day become part of new worlds and new possibilities. Yet even as galaxies collide and merge, not all of their stars are destined to become part of the new, blended structure. In the chaotic gravitational turmoil of these encounters, a remarkable escape occurs. The same immense forces that pull galaxies together can also act as a cosmic catapult, flinging individual stars out into the vast, empty intergalactic void at speeds so tremendous they can never return. These are the hypervelocity stars, and their discovery has opened a thrilling new window into the most violent chapters of our galaxy's past. The concept is as elegant as it is powerful. Picture the supermassive black hole that resides at the very heart of our Milky Way, a gravitational monster weighing in at 4 million times the mass of our Sun. When a binary star system, two stars orbiting a common center of gravity, wanders too close to this behemoth, a gravitational slingshot of epic proportions can unfold. The black hole's incredible gravity can tear the binary pair apart. One star gets captured into a tight, whirling orbit around the black hole, while its companion is suddenly set free, hurtled away at a significant fraction of the speed of light, as if launched from an unimaginably powerful sling. This three-body interaction converts the orbital energy of the binary system into raw kinetic energy for the ejected star, propelling it on a one-way journey out of the galactic core. The first of these cosmic fugitives was discovered in 2005, a massive star speeding through the outskirts of our galaxy at over 2 million miles per hour. At that velocity, it was moving fast enough to completely overcome the Milky Way's gravitational pull, destined to fly free into intergalactic space forever. Since then, dozens of these hypervelocity stars have been identified, and their trajectories are like forensic evidence, pointing backward in time to the violent events that created them. While the supermassive black hole at our galactic center is the most efficient engine for producing these stars, it's not the only one. Galactic collisions, like the ancient merger with the Gaia-Enceladus galaxy, can also generate hypervelocity ejections on a much broader scale. In the messy, gravitational dance of two merging galaxies, Stars can receive gravitational kicks from dense clusters or from the combined tidal forces of the interacting systems, sending them flying on new, high-speed trajectories. These stars become lonely travelers, solitary beacons illuminating the dark spaces between galaxies, carrying with them the chemical signature of their original home. By studying their speed, composition, and path, astronomers can trace them backward, often finding that their point of origin aligns with known sites of past galactic violence, effectively using them as tracer bullets to map out long-finished cosmic battles. The existence of these stars profoundly changes our understanding of the galactic ecosystem. For a long time, we imagined stars as largely bound to their host galaxies, tracing orderly orbits within a vast, rotating disk. Hypervelocity stars shatter that peaceful image. They reveal that galaxies are not closed systems. They can both gain and lose stars through dramatic gravitational interactions. This stellar ejection process also has implications for the evolution of galaxies themselves. When a high-mass, hypervelocity star is flung out, it carries its heavy elements with it, effectively removing that enriched material from the galactic core and depositing it into the galactic halo or the intergalactic medium. This is a form of galactic feedback, a way for the intense environment around a central black hole to influence the chemical distribution of the wider galaxy. Furthermore, the discovery of these stars provides indirect but compelling evidence for the presence of a supermassive black hole at the Milky Way center, as their observed velocities and trajectories perfectly match the predictions of the binary disruption model. They are, in a very real sense, living proof of the terrifying gravitational power that lurks in the heart of our own galaxy, a power that can, with a single gravitational flick, send a star on a million-year journey into the endless dark. Zooming in from the grand collisions of galaxies and stars, we come to the very cradle of planets, the swirling, dusty nurseries known as protoplanetary disks. These vast, pancake-shaped clouds of gas and dust that orbit young stars are where worlds are born. The classic image might be one of serene, gentle accumulation, where dust grains peacefully stick together to eventually form planets. But the reality of planet formation is far more chaotic and violent. It is a story dominated by relentless, high-speed collisions that determine which bodies survive and which are utterly annihilated. This process, known as runaway accretion, is the chaotic construction zone where the foundational blocks of solar systems are forged through impact. It all begins with the finest of materials. In the aftermath of a star's formation, the leftover material in the disk consists of microscopic dust grains, silicates, ices, and flecks of carbon. In the calm, dense midplane of the disk, these grains begin to bump into each other, initially sticking through weak electrostatic forces, a process called coagulation. They form fluffy, fractal aggregates like cosmic dust bunnies, but this gentle sticking only gets you so far, perhaps to the size of pebbles or small rocks. The pivotal shift occurs when these objects grow large enough, roughly a kilometer across, to become what scientists call planetesimals. At this scale, their own gravity becomes significant. No longer relying on static cling, they begin to exert a gravitational pull on their neighbors, drawing in more material and turning the construction process into a competitive, high-stakes game of gravitational billiards. This is where the chaos truly erupts. Within the crowded disk, countless planetesimals are on intersecting orbits, crossing paths at speeds of several kilometers per second. When they meet, the outcomes vary dramatically based on their size, angle, and relative velocity. Some collisions are gentle enough to be constructive. Two bodies merge, their masses adding together to form a larger, more massive object called a planetary embryo. These embryos, the precursors to full-fledged planets, act as gravitational anchors in their local region, their growing mass allowing them to dominate and clear their orbital lane. However, for every merger that builds a new world, there are countless destructive impacts. High-speed collisions can shatter planetesimals back into rubble, vaporizing rock and metal and resetting the growth process. Others might be grazing impacts, chipping off large pieces or creating swarms of new debris. The entire inner disk becomes a chaotic shooting gallery, a continuous cycle of destruction and assembly where only the most fortunate or resilient bodies grow. The term runaway accretion perfectly captures the frenzied, exponential nature of this growth. Once an embryo gains a slight mass advantage over its neighbors, its gravitational reach increases, allowing it to sweep up material from a wider area more quickly. It's a classic case of the rich getting richer. The largest embryo in a given feeding zone begins to consume its smaller competitors at an accelerating rate, snowballing in size. In the inner, hotter part of the disk where rocky materials can survive, this process builds the terrestrial planets Mercury, Venus, Earth, and Mars. This was not a slow, stately dance, but a violent, winner-take-all battle for material that lasted for tens of millions of years. The final stages of Earth's own formation, for instance, were marked by colossal impacts with other planetary embryos, the most dramatic of which was the collision with Theia that gave us our moon. This means our planet's very existence is the product of a final, spectacular merger that capped off eons of violent collisional growth. The evidence for this violent birth is etched into the very fabric of our solar system. The pockmarked surface of the Moon, Mercury, and Mars preserved from the early solar system stand as silent testimony to this final bombardment phase. The different compositions of the planets also tell a tale of collisional history. For example, Mercury's enormous iron core suggests a colossal impact might have stripped away much of its rocky mantle, leaving behind a metallic remnant. The asteroid belt itself is a relic of this era, a region where the gravitational influence of Jupiter prevented a planet from forming, leaving behind a population of primordial planetesimals that continue to collide to this day, sending fragments to Earth as meteorites. By studying these space rocks, we hold in our hands the very building blocks that never got incorporated into a major planet, frozen in time from the solar system's most violent and creative chapter. The peaceful order we see in our solar system today is the calm after an epic storm, the settled dust from a construction project of unimaginable fury that built every world we call home. But when we look at Mars today, we don't just see the ghost of a planetary trauma in its two-faced surface. We see two enigmatic companions tumbling through the crimson sky, Phobos and Deimos. For a long time, these two small, lumpy moons were a profound puzzle. Their bizarre appearance and unusual orbits led many scientists to believe they were simply asteroids captured by Mars' gravity long ago. Yet, as we studied them more closely, that simple explanation began to unravel, pointing toward a far more dramatic and familiar origin story. This brings us to our 22nd massive cosmic collision, the cataclysmic impact that likely gave birth to the moons of Mars, an event that mirrors the birth of our own moon but with a strikingly different outcome. The captured asteroid theory certainly had its appeal. Phobos and Deimos are small, dark, and irregularly shaped, much like the asteroids that populate the belt between Mars and Jupiter. Their surfaces are covered in a dark, carbon-rich material that reflects very little light, which is a common trait of a specific class of asteroids known as carbonaceous chondrites. If Mars had simply snagged two passing asteroids from the nearby belt, it would have been a tidy conclusion. However, the orbits of these moons tell a completely different story. Both Phobos and Deimos orbit Mars in almost perfect circles and in the same plane as the planet's equator. This is highly unusual for captured objects. When a planet's gravity captures a passing asteroid, the resulting orbit is typically a wide, stretched-out ellipse tilted at a random angle. The neat, orderly, and equatorial paths of Phobos and Deimos are exactly what you would expect if they formed from a disk of debris that was orbiting a young Mars, a disk that would naturally settle into the planet's equatorial plane. This single critical observation was the first major clue that their origin was not one of accidental capture, but of direct creation. This is where the giant impact hypothesis comes into play, providing an elegant solution that ties together the Moon's strange characteristics with the violent history of Mars itself. The leading model suggests that after the colossal Borealis impact that carved out the northern plains, Mars was struck again. This second giant impact, while smaller than the first, was still monumental. A protoplanet, perhaps 1/10 to 1/100th the mass of Mars, slammed into the young planet. The energy of this collision would have been sufficient to blast an enormous quantity of Martian crust and mantle, along with material from the impactor itself, into space. Just as with Earth and Theia, this ejected material would have formed a vast, hot disk of vaporized rock and debris encircling Mars, a structure known as a circumplanetary disk. Within this tempestuous disk, the physics of accretion began to work. Particles collided and stuck together, slowly growing from dust grains into larger and larger bodies. But here, the environment was very different from the one that surrounded the infant Earth. Mars is a much smaller planet with only about 1/10 of Earth's mass. This means its gravity is significantly weaker. In this lower gravity environment, the debris disk would have been less dense and spread out over a wider area. The process of moon formation would have been less efficient, preventing a single, large moon from coalescing. Instead, the material in the disk clumped together into several smaller moonlets. Over time, gravitational interactions between these moonlets would have thrown many of them back into Mars or out into space, leaving behind only the two most stable survivors, Phobos and Deimos. This scenario beautifully explains their small size and their current locations. The material for the moons came predominantly from the Martian crust, which is why spectral analysis suggests their composition is similar to the surface rocks of Mars, yet altered by the intense heat of the impact. The distinct fates of these two sibling moons further reveal the dynamic history of this system. Phobos, the larger and inner moon, orbits so close to Mars that it whips around the planet 3 times a day. It is gradually spiraling inward due to tidal interactions, and in about 50 million years, it will either crash onto the Martian surface or be torn apart by gravitational forces to form a ring around the planet. Deimos, on the other hand, orbits farther out and is slowly drifting away. This divergence in their destinies is a direct consequence of their formation from a disk. Different starting locations in the original debris ring lead to different gravitational pressures and tidal evolution. The very fact that we can predict their future paths based on this model adds tremendous weight to the giant impact theory. Upcoming missions, like the Japanese Space Agency's Martian Moons e-exploration mission, aim to visit Phobos and Deimos, collect samples, and bring them back to Earth. Analyzing the precise composition of these moons will be the ultimate test. If they are indeed captured asteroids, their material will be alien to Mars. But if they are the children of a giant impact, their chemical fingerprints will match those of the Martian crust, finally confirming that the red planet's most intimate companions were born from one of the most violent events in its history. Now, let's turn our attention to the planet of love, but a world that hides a truly hellish and backward secret. Venus presents us with one of the most perplexing anomalies in our entire solar system. While nearly every other planet spins counterclockwise when viewed from above the Sun's north pole, Venus defiantly spins in the opposite direction, a slow, backwards rotation known as retrograde. A single day on Venus, the time it takes to complete one rotation, is longer than its entire year, lasting 243 Earth days. So, how did our nearest planetary neighbor end up so topsy-turvy? The most compelling explanation points to a cataclysm of monumental force. The leading hypothesis suggests that in the chaotic early solar system, a protoplanet or massive planetary embryo, perhaps 1/3 the size of Venus itself, slammed into the young world. This was not a gentle glancing blow. It was a colossal impact that struck with such force and at such a precise angle that it effectively stopped Venus's original spin and sent it spinning in the opposite direction, like hitting a spinning top with a hammer to reverse its motion. An alternative, equally dramatic model proposes the impact didn't just slow and reverse the spin, but literally flipped the entire planet upside down by 180 degrees. In this scenario, Venus's current north pole was once its south pole, meaning it never technically reversed its spin relative to the universe. It was just turned completely over, creating the appearance of retrograde rotation from our perspective. This single defining collision didn't just alter Venus's spin. It set in motion a chain of events that would transform the planet from a potential twin of Earth into a scorching, toxic inferno. The immediate aftermath of the impact would have been apocalyptic. The energy released would have vaporized any early oceans and stripped away a significant portion of the planet's primordial atmosphere. More profoundly, the impact likely dealt a death blow to Venus's internal magnetic dynamo. Just as with Mars, a planet's global magnetic field is generated by the churning of a molten conductive core. The cataclysmic shock and the transfer of immense angular momentum from the impact could have severely disrupted the convective motions within Venus's core, causing its magnetic field to collapse. Without this protective magnetic shield, Venus was left utterly exposed to the full fury of the solar wind. This relentless stream of charged particles from the Sun began a multi-billion-year assault, steadily stripping away lighter atoms from the atmosphere, particularly hydrogen, which is a key component of water. This process, while slow, was inexorable, and it fundamentally changed the chemical balance of the planet. The loss of a global magnetic field was the first critical step toward the runaway greenhouse effect we see today. With no shield, the solar wind could interact directly with the upper atmosphere, but the true climatic catastrophe was yet to come. As the young sun grew brighter, Venus, being closer to the sun than Earth, received more intense solar radiation. Any remaining surface water would have begun to evaporate dramatically. Water vapor is a potent greenhouse gas, and as more of it entered the atmosphere, it trapped more and more heat, raising the surface temperature. This caused even more water to evaporate, creating a powerful positive feedback loop. At a certain tipping point, the oceans would have reached a full, rolling boil, and the water vapor atmosphere became so thick that it allowed solar radiation in but prevented the infrared heat from escaping back into space. The surface temperature soared, eventually becoming hot enough to bake the carbon dioxide out of the surface rocks. On Earth, our carbon dioxide is safely locked away in carbonate rocks like limestone, a process regulated by our water cycle and plate tectonics. On Venus, the superheated atmosphere prevented this sequestration. Vast quantities of carbon dioxide were outgassed from the crust and poured into the air, turning the atmosphere into an overwhelmingly dense, suffocating blanket of CO2. This sealed the planet's fate, triggering the ultimate runaway greenhouse that created the crushing 900°C surface we observe today. When we look at Venus now, we are seeing the long-term legacy of that ancient violence. The incredibly slow rotation, a direct result of the impact, has bizarre consequences for the Venusian climate. A single solar day on Venus from one noon to the next takes 116 Earth days because the slow retrograde rotation combines with the planet's orbital motion. This means the surface is baked by the Sun for nearly 2 straight Earth months at a time, contributing to the planet's intense and uniform heat. Furthermore, the lack of a magnetic field and the resulting atmospheric erosion meant that Venus could never hold onto the hydrogen needed to keep its water. What little water vapor remains in the atmosphere today shows a telltale signature of this historical loss, an enrichment of deuterium, a heavier hydrogen isotope. As the solar wind stripped away the lighter hydrogen atoms, the heavier deuterium was left behind, creating a higher concentration, a forensic clue pointing to the disappearance of a once vast ocean. The story of Venus is a sobering cautionary tale about planetary destiny. It demonstrates with brutal clarity how a single, random collision in the early solar system can set a world on a completely different evolutionary path. Had that impactor missed, Venus might have retained its magnetic field, its oceans, and perhaps even its potential for life, truly becoming Earth's sister. Instead, it stands as a stark monument to the role of cosmic chance, a world whose hellish present was forged in the fiery violence of its past. But to truly understand the final resting places of these icy wanderers, we first need to journey back to the chaotic construction zone of our early solar system. Imagine the scene just after the sun ignited, a vast, swirling disk of gas and dust teeming with countless icy and rocky bodies called planetesimals. These were the leftover building blocks, the raw materials that didn't get incorporated into the planets themselves. In the inner solar system, closer to the sun's warmth, these bodies were mostly rock and metal, which eventually formed the terrestrial planets. But beyond the frost line, a boundary where temperatures were cold enough for volatile compounds like water, methane, and ammonia to freeze solid, space was dominated by countless icy planetesimals. This is where the story of our solar system's deep freeze begins, a tale of gravitational chaos that created two distinct cosmic reservoirs. The young giant planets Jupiter, Saturn, Uranus, and Neptune were the undisputed masters of this outer realm, and their immense gravity acted like a cosmic pinball machine. As these planets migrated and settled into their orbits, their gravitational influence sent the surrounding icy planetesimals careening in all directions. The fate of any individual ice ball depended entirely on its close encounter with a giant. A gentle gravitational nudge might simply alter its orbit slightly. But a close pass by a planet like Jupiter was a game changer. Jupiter's colossal gravity could act as a powerful slingshot, hurling these objects on trajectories with such immense energy that they could achieve escape velocity from the sun's grasp entirely, being ejected into interstellar space to become rogue nomads wandering the galaxy. However, many more received a different fate, a powerful kick that sent them flying out to the extreme fringes of the sun's gravitational influence, but not quite enough to grant them full freedom. These objects became the inhabitants of the Oort Cloud, a vast spherical shell of icy bodies thought to begin roughly 2,000 astronomical units from the sun, and extending outward to perhaps a light year or more, reaching about a quarter of the way to the next star. Simultaneously, a different gravitational dynamic was at play farther in. While Jupiter was the primary engine for flinging objects to the Oort Cloud, the collective influence of all the giant planets, particularly Neptune, sculpted a closer-in region. As Neptune migrated outward in its early history, its gravity shepherded a vast population of icy bodies into a disk-like zone beyond its orbit. These objects, unable to coalesce into a planet due to Neptune's gravitational stirring, found stable orbits in a region we now call the Kuiper Belt. This is essentially a vast, donut-shaped ring of icy worlds stretching from the orbit of Neptune out to about 50 astronomical units from the Sun. So, while both are reservoirs of primordial ice, the Oort Cloud and the Kuiper Belt are products of different scattering processes and exist in fundamentally different structures, one a distant spherical halo, the other a relatively flat, ring-like belt closer to home. The existence of these two frozen archives is a direct, observable consequence of those ancient gravitational collisions. We can think of them as the solar system's attic and basement, storing the leftover building materials from its construction. The Kuiper Belt is our more accessible archive, and its study has revolutionized our understanding of the outer solar system. The discovery of Pluto as just one of many large Kuiper Belt objects redefined our planetary family. Missions like New Horizons, which flew past Pluto, and the subsequent Kuiper Belt object Arakoth, gave us our first close-up look at these pristine remnants. Arakoth, in particular, with its stunning two-lobed snowman shape, looks exactly like two separate planetesimals that gently merged together in the solar system's earliest days, a frozen snapshot of the very accretion processes that built the planets. The Oort Cloud, by contrast, is far more elusive. It is too distant and its objects too faint for us to observe directly with current technology. Instead, we infer its existence through the behavior of long-period comets. These are the spectacular, unpredictable visitors that swoop in from any direction in the sky, with orbits that can take tens of thousands or even millions of years to complete. Their random orbital inclinations are the key clue. A flat, disk-like structure like the Kuiper Belt would only produce comets with orbits close to the plane of the solar system. The fact that long-period comets arrive from all angles points to a spherical source, the Oort Cloud. A chance gravitational nudge from a passing star or the tidal force of the galaxy itself can dislodge one of these icy fossils, sending it on a long fall inward toward the Sun, where it heats up and blossoms into the glowing comet we see in our night sky. Every time we witness a long-period comet, we are effectively looking at a messenger from the solar system's birth. These icy bodies have been in deep freeze for 4.5 billion years, preserving the original chemical conditions of the protoplanetary disk. They are time capsules that have never been heated or geologically processed, carrying within them the pristine ices and organic compounds that were present when our planetary system first formed. The gravitational pinball game that flung them to the outskirts was a violent and chaotic process, but it had a profound benefit for us. By scattering these icy planetesimals, the giant planets effectively stored them away in a cosmic freezer, safeguarding a record of our origins and occasionally sending us a reminder in the form of a beautiful, glowing visitor that has traveled from the absolute edge of the Sun's dominion to grace our skies. And so we arrive at our final monumental collision, one that is unique because it is happening right now and will continue for as long as our planet exists. This is not a single cataclysmic event from the distant past, but a continuous, gentle rain of cosmic material that connects us in every moment to the wider solar system. We live under a constant, silent shower of space dust. Every single year, our planet gains between 40 and 100,000 tons of extraterrestrial material. The vast majority of this arrives as tiny micrometeoroids, particles smaller than a grain of sand. As they enter the atmosphere at hypersonic speeds, they don't create dramatic fireballs. Instead, they vaporize silently, high above the clouds, leaving behind a faint, lingering residue of metallic atoms like iron and nickel. This cosmic dust slowly settles through the air, eventually mixing with the rain and snow to become a part of the very ground we walk on. It's a humbling thought that with every breath you are likely inhaling atoms that were once part of an asteroid or a comet, a subtle but perpetual reminder that our world is not an isolated island, but an integral part of a dynamic and dusty cosmic ecosystem. Of course, not all of this ongoing bombardment is invisible. While the daily dustfall goes unnoticed, our atmosphere is frequently lit up by more dramatic visitors. These are the fireballs or bolides caused by larger objects, typically ranging from the size of a pebble to a small boulder. When these enter the atmosphere, the friction with the air creates a brilliant streak of light, often outshining the planet Venus and sometimes even appearing in broad daylight. Networks of all-sky cameras like NASA's All-Sky Fireball Network are constantly monitoring the skies, triangulating the paths of these objects to calculate their original orbits and even pinpoint where any surviving meteorites might land. These fireballs are far more common than most people realize. Estimates suggest that several thousand occur in Earth's atmosphere each year that are bright enough to be seen in daylight. Most of these objects completely disintegrate, but they provide a spectacular, real-time demonstration of the protective power of our atmosphere, which acts as a robust shield, vaporizing the vast majority of what comes our way. This brings us to the critical present-day work of planetary defense. The Chelyabinsk event in 2013 was a powerful wake-up call, proving that objects large enough to cause regional devastation can arrive without any warning. In response, a global network of astronomers and engineers has dedicated themselves to the monumental task of finding and tracking near-Earth objects, or NEOs. These are asteroids and comets whose orbits bring them within about 30 million miles of Earth's path around the Sun. The goal is simple in concept but daunting in practice: to find them before they find us. Using powerful ground-based telescopes like the Pan-STARRS system in Hawaii and the Catalina Sky Survey in Arizona, automated systems scan the heavens night after night, looking for the faint, star-like points of light that move against the background of fixed stars. When a new NEO is discovered, its path is meticulously calculated to determine if it poses any future impact risk. The process of risk assessment is a sophisticated exercise in orbital mechanics and probability. It's not enough to simply know an asteroid is there. We need to predict its path decades or even a century into the future. This is incredibly difficult because an asteroid's orbit is constantly being minutely perturbed by the gravity of other planets, the subtle push of solar radiation, and even the thermal influence of the Sun itself. To handle this uncertainty, scientists use a scale called the Palomar-Technical Impact Hazard Scale, which combines the probability of an impact with its estimated kinetic energy. You may have also heard of the Torino scale, which is a simpler, color-coded system designed for public communication, ranging from 0 for no hazard to 10 for a certain global catastrophe. For an object to be of serious concern, it must be large enough to cause significant damage generally. Anything over 140 meters in diameter is considered a priority, and its calculated path must show a non-zero probability of intersecting with Earth. The good news is that the vast majority of newly discovered objects are quickly assessed and assigned a value of 0 on the Torino scale, meaning they pose no risk. The challenge lies in finding the ones that do, especially those that, like the Chelyabinsk meteor, approach from the sunward direction where they are hidden in our telescope's blind spot. This is why the future of planetary defense lies in space. Upcoming missions are designed to close this critical observational gap. NASA NEO-Surveyor is a dedicated space telescope scheduled to launch in the late 2020s. Its infrared eyes will be able to detect the heat signatures of asteroids, making it exceptionally good at finding those that are currently invisible to us because they lurk in the direction of the Sun. By conducting its survey from the stable environment of space, free from the distorting effects of Earth's atmosphere and the cycle of day and night, NEO-Surveyor aims to find at least 90% of the NEOs larger than 140 meters within a decade. But finding them is only the first step. What do we do if we actually find a dangerous object on a collision course? This is no longer the stuff of science fiction. In a historic test of our technological capability, NASA's DART mission, the Double Asteroid Redirection Test, successfully slammed a spacecraft into a small moonlet called Dimorphos, which was orbiting a larger asteroid named Didymos. The goal was not to destroy the object, but to give it a carefully calculated nudge, just enough to change its orbital period. The result was a spectacular success. The impact shortened Dimorphos's orbit by a significant 33 minutes, far exceeding expectations. This proved that the kinetic impactor technique is a viable method for planetary defense, giving us a tangible tool to alter the trajectory of a threatening asteroid, provided we have enough lead time. The ongoing cosmic rainfall and our efforts to understand it complete our journey through the collisions that shaped the universe. From the primordial fire of the Big Bang to the gentle dust settling on your rooftop today, the story of our cosmos is written in impact. These collisions are the architects of planets, the deliverers of water and life, the forces behind mass extinctions and evolutionary resets, and the builders of galaxies. They are both creative and destructive, agents of chaos and architects of order. We have traced their fingerprints on the scarred face of Mercury, in the tilted spin of Uranus, in the glittering rings of Saturn, and in the ancient craters of our own moon. We have seen how they forge gold in the hearts of colliding neutron stars and how they fling stars from their galactic homes. And now we see them in the silent dust and occasional fireballs that remind us that this cosmic construction project is far from over. Our planet and the life upon it is a product of this endless dynamic interplay. By looking up and vigilantly mapping our cosmic neighborhood, we are not just seeking to avoid a fate like the dinosaurs. We are embracing our role as conscious participants in this ongoing story, using our intelligence and ingenuity to ensure that the next great collision is not an end, but merely another chapter in the long and spectacular history of our universe. As we've journeyed through these cataclysmic events, from the violence of the early solar system to the mergers of distant galaxies and neutron stars, one profound truth emerges: these collisions were not merely agents of destruction. They were the fundamental creative engines of the cosmos, the very forges that crafted the conditions necessary for life to arise and flourish. Think of it this way: our universe began with the simplest of recipes, the hydrogen and helium forged in the Big Bang. But for a universe to become complex, to build planets and oceans and living beings, it needed a way to cook up heavier ingredients. That's where the life cycle of stars and their spectacular deaths came in. Within the fiery cores of massive stars, nuclear fusion acted as a cosmic pressure cooker, relentlessly squeezing atoms together to create elements like carbon, oxygen, and nitrogen. But this process alone could only go so far, stalling at iron. To build the rest of the periodic table, the universe required something far more violent: the supernova explosions that tore these stars apart, and the even more intense collisions between their ultra-dense remains, the neutron stars. It was in these unimaginable blasts, these fleeting moments of ultimate chaos, that the universe forged the gold, silver, iodine, and uranium that would later become part of our world. The very atoms that form the backbone of our DNA, the iron that carries oxygen in our blood, and the calcium that strengthens our bones were all smelted in these stellar furnaces and scattered across the galaxy by titanic explosions. Yet, creating the elements was only the first step. These precious materials needed to be delivered and assembled into a stable, habitable environment. This is where planetary-scale collisions entered the stage as the great architects of our cosmic neighborhood. The impact that gave Earth its moon was far more than a dramatic crash. It was a pivotal event that set our planet on a unique course. By spinning off a large satellite, that collision gifted Earth with a stable axial tilt. Without the moon's steadying gravitational hand, our planet's tilt would wobble wildly over time, leading to chaotic and extreme climate swings that would make the long-term, stable environmental conditions required for the evolution of complex life virtually impossible. Furthermore, the energy of that impact likely remelted Earth's interior, kick-starting the plate tectonics that continually recycle our planet's crust, regulate our climate over eons, and create the diverse geology that supports a rich biosphere. At the same time, the period of the late heavy bombardment, while appearing to be a time of sheer devastation, was in fact a celestial delivery service. Icy comets and water-rich asteroids pummeling the young Earth did not just leave craters, they brought the oceans. They delivered not only the water that fills our seas, but also the complex organic molecules, the amino acids and other prebiotic compounds that served as the raw building blocks for the first living organisms. The violence that once threatened to sterilize our world ultimately provided the very water and chemistry that allowed life to spark into existence. When we step back and connect all these dots, a breathtaking narrative unfolds, one that intimately connects each of us to the most energetic events in the history of the universe. Every single atom in your body has a cosmic pedigree that stretches back billions of years. The hydrogen in the water you drink is a primordial relic, a direct descendant from the Big Bang itself. The carbon that forms the framework of your every cell was fused in the heart of a long-dead star. The oxygen you breathe was likely blasted into space by a supernova. The iron coursing through your veins was forged in the final moments of a massive star's life, and the iodine essential for your metabolism was almost certainly created in the furious collision of two neutron stars. You are, in the most literal sense, a collection of cosmic artifacts, a walking museum of the universe's most violent and creative moments. This perspective transforms our understanding of our place in the cosmos. We are not separate from the universe. We are a conscious expression of its dynamic and often violent processes. The same forces that carved craters into moons, that tilted planets on their sides, and that ripped galaxies apart are the very same forces that assembled the complex chemistry that allows us to exist, to think, and to look up at the night sky in wonder. Our existence is the most compelling evidence that in the grand cosmic balance, creation and destruction are two sides of the same coin, and that from the deepest chaos can emerge the most profound beauty and complexity. And so we reach the end of our voyage, a journey spanning the entirety of cosmic history from the first fraction of a second to the distant future. We've witnessed 25 monumental collisions, each a testament to the raw, untamed power that built everything we know. From the genesis of space-time in the Big Bang to the galactic wreckage of the antennae, from the planetary-scale impacts that carved our moon and scarred Mars to the neutron star mergers that forged the gold in our jewelry, one unifying theme has emerged with stunning clarity. The universe is not a place of serene, quiet order. It is a dynamic, chaotic, and often violent arena where creation and destruction are locked in an eternal, intimate dance. The very same cataclysms that can end a world are the very forces that built it, that filled its oceans, that stabilized its climate, and that seeded it with the chemistry of life. This is the great cosmic paradox that from the deepest chaos emerges the most profound beauty and complexity. Think about the legacy these events have left, not just in the distant heavens, but right here in your own existence. The iron in your blood, the calcium in your bones, the very air you breathe, all of it is stardust forged in the hearts of stars and scattered across the galaxy by titanic explosions and collisions. You are a living, breathing collection of cosmic artifacts, a walking museum of the universe's most energetic moments. That connection is not just metaphorical, it is the literal story of your atomic ancestry. When you look up at the moon, you are seeing the scar of a planetary disaster that gave us stable seasons. When you admire a piece of gold, you are holding a material born in a blizzard of neutrons from a stellar collision a billion years ago. Our entire world and our place upon it is the direct and miraculous result of this relentless cosmic construction project. This perspective invites a profound shift in how we see our place in the cosmos. We are not mere spectators isolated on a pale blue dot. We are an active, conscious expression of the universe itself, a product of its dynamic processes now able to look back and understand its own origins. The violence that shaped the galaxies is the same force that, through a long and intricate chain of events, led to you being here to watch this video. It's a humbling and empowering realization that we are part of something infinitely larger and more magnificent than our daily concerns. Now we turn this profound story over to you. The night sky is no longer just a collection of pretty lights. It is a living history book, its pages filled with tales of cosmic violence and glorious rebirth. So the next time you find yourself under a clear, dark sky, take a moment, look up. Let your imagination travel to the impact that carved the lunar seas, to the silent dance of galaxies slowly merging, to the invisible rain of stardust settling on your skin. Remember the epic journey that connects those distant events to the very core of your being. We'd love to continue this conversation with you. In the comments below, tell us which of these 25 cosmic collisions you found the most awe-inspiring, the most terrifying, or the most beautiful. Was it the sheer power of the Big Bang, the dramatic birth of our moon, the dinosaur-ending Chicxulub impact, or the golden forges of colliding neutron stars? Share your thoughts and let's explore the wonders of our violent, creative, and breathtakingly beautiful universe